Okay, today we are going to solve the governing differential equation of your cantilever bar. Before we get straight into the business of deriving the governing differential equation, let us ask this question. Why do you want to derive the governing differential equation in the first place? So once you have derived the governing differential equation, what is the use? Well, if you have the governing differential equation, you can solve the governing differential equation and you can extract valuable information by solving the governing differential equation. In our case, you can solve the governing differential equation of your cantilever bar and you can extract the information of displacement of the cantilever bar at any position of the bar. At any point in the bar, you can tell what is the value of displacement without measuring the displacement practically. So that is a tremendous advantage of solving the governing differential equation. So you can extract that information that is vital to make smart engineering decisions. So that is the reason why we have to solve the governing differential equation of your cantilever bar. So first let me draw a cantilever bar. So you can see that I am drawing a cantilever bar. Now you may ask me this question, is it not a cantilever beam? That looks like a cantilever beam. So what is the difference between a bar and a beam? The difference is very subtle. In the case of a bar, the load will act along the axial direction, whereas in the case of a beam, the load acts in the transverse direction. So that is a subtle difference between a bar and a beam. So in the case of a bar, the load is acting along the axis of the structure. In the case of a beam, the load acts transverse to the structure. So I have got a cantilever bar. So one end of the structure is built into the wall, one end of the bar is encasted into the wall. So let me define the geometric properties of this cantilever bar. This cantilever bar has got a length of magnitude L, and it has got a cross-sectional area of magnitude A. So length and the area are geometric properties. And this cantilever bar is made up of material that has got an Young's modulus value of magnitude capital E. So you see that it is a material property because it varies from one material to another material. If this bar is made up of steel, it has the Young's modulus value of steel. If the bar is made up of aluminum, it will have the Young's modulus value of aluminum. So since the Young's modulus varies from one material to another material, Young's modulus is material property, whereas length and area depends on the geometries of the particular structure that is under investigation, and that is the reason why they are called as geometric properties. Now, what is the stuff that is acting on this cantilever bar? This cantilever bar is subjected to uniformly distributed axial load. So I am using this red color to indicate the uniformly distributed axial load that is acting on this cantilever bar. And that stuff that is acting on this cantilever bar, this uniformly distributed axial load, that is Q. Its unit is Newton per unit length. It may be Newton per meter or it may be Newton per mm, depending on whatever unit is conducive to express. For example, if the value is 10 Newton per mm, it means over a span of 1 mm, the total load that is acting is 10 Newton. That's the meaning. Now what I'm going to do is I'm going to consider a small structure. I'm going to localize my attention on a small structure. So that's what I'm going to do. I'm going to localize my attention on a small structure here of length dx at a distance x from the left hand side. At a distance of x from the left hand side, I'm going to consider a small structure and I'm going to localize all my attention on this small portion of the bar. So I will just take out the small portion and I will draw the small portion in an amplified way. So This is the small structure that is under investigation. Now what I'm going to do is very simple. I'm going to ask myself this question: what is the stress that is acting on this small portion that we have considered of length dx? If this board has a square or rectangular cross section, it will look something like this. It need not be always a square or rectangular cross section. It can be even circular in cross section. So just to get across the concept in a conducive way, I'm just assuming that the structure is square, the cross section is square. So I have drawn the structure that way. So what I'm going to do is I'm going to define the stress on this small portion. So what is stress? Well, stress is load by area. Now the question here is, what is the load that is acting on this small portion? What is the load that is acting on this small portion? Is it what? What is the load? So the load that is acting on the small portion is Q into L minus X. That is the load, divided by the cross-sectional area is A. So the next question here is, how do you say that the load that is acting on the small portion is Q into L minus X? How can we say that? I'm going to give an explanation here. This distance here is L minus X. Now you may say that this distance is actually L minus X plus dx. You may say that this distance is L minus X plus dx, but this dx value is very small that we can ignore it without incurring any serious error in mathematics. So you can safely ignore it, even if you consider that the effect produced by this dx is very, very small. It is infinitesimally small. It is vanishingly small. So for all practical purposes, we can ignore the effect of dx without incurring any serious error in mathematics. Now the total load that is acting on the small portion is the total load that is acting in this region. So that is the total load that is acting on the small portion. Here, the total load is acting on the total load that is acting on the small portion here is the total load that is distributed over here. Now, in order to understand this concept, in an intuitive manner, I'm going to draw a structure here. Just imagine that you are clinging onto a ceiling. So I'm going to draw a diagram here. Just forgive me if the diagram is poor. Now imagine that you are clinging onto the ceiling, and imagine that your friend is hanging onto the foot of you. So here is your friend hanging onto the foot of you, and you are clinging onto the ceiling. And there is a third person who is clinging onto the foot of the second person. And there is a fourth person who is clinging onto the foot of the third person. And there is a fifth person who is clinging onto the foot of the fourth person. Now, if you look at this particular diagram, the first person here should experience all the weight of all the four persons beneath him, including his self-weight. And the second person, this guy here, should experience the weight of all the three persons beneath him, including his self-weight. And the third person here should experience the weight of all the two persons beneath him, including his self-weight. So on and so forth. Interesting point here is, what about the weight experienced by the last person? That guy should experience only his self-weight. He should not be experiencing the weight of all the four persons above him. That person should experience only his self-weight, this person. Interesting point here is, what about the weight that is experienced by the foot of the last person? What about the weight stress that is experienced by the foot of the last person? Well, if you just exercise it in your imagination, you will get an intuitive feel that the foot of the last person, this guy here, should not experience any weight at all. Just imagine, he should not be experiencing any weight at all. It is exactly the same scenario for your bar. If this is the small portion dx that we are considering, this small portion dx should experience the weight of all the persons beneath this particular guy. And therefore, this small portion here should experience the weight of all the load that is acting onto the right hand side of this small portion. And what is the load that is acting on the right hand side of this small portion? It is q into L minus x, because q is, its unit is, let us say for example, Newton per meter. So for a distance of 1 meter, the total load is, for a distance of, I will write that here, for a distance of 1 meter, the total load is q newtons. So what would be the total load for a distance of, that is acting over a distance of L minus x meters? So you just have to cross multiply to find the unknown, and that unknown will become q into L minus x. So that is the total load that is acting on this small portion. That's how you define stress. Now I'm going to define the strain. Strain is change in length divided by original length. Let us say that this point here is getting displaced along the x direction by an amount u1, and this point here, because of the load acting along the x direction, is getting displaced by an amount u2. Now I can define something called a strain. Strain is u1 difference u2, which is change in length, divided by original length, which is dx. u1 difference u2 is simply du by dx. Mathematicians will not allow me to do this way right away, but anyway, it is del u by del x. When del u becomes very small, it becomes du. So mathematicians will not allow me to do this step right away, but anyway, I have done that. Strain is du by dx. Having defined the stress on the small portion and the strain on the small portion, I can define something called as Young's modulus. What is Young's modulus? It is stress by strain, stress divided by strain. So Young's modulus is stress is q into L minus x divided by A. I got that value from here. We have got the value of stress. Strain is du by dx. So Young's modulus divided by, for strain, I can simply put this value of du by dx, du by dx. So I can rearrange this equation, and I can rewrite this equation mathematically. I'm just going to rearrange this equation. So mathematics is just like arranging objects. It is AE into du by dx is equal to q into L minus x. I have just rearranged the equation mathematically. So I'm going to differentiate this equation with respect to x. So differentiate this equation with respect to x once. So what is that you're going to get? AE into d squared u by dx squared. This right hand side, if you differentiate this L, it becomes 0. If you differentiate x with respect to x, you get 1. So already there is a negative here. So it is minus 1 into q. That becomes minus q. So I can rearrange this particular equation as AE into d squared u by dx squared plus q is equal to 0. That is the governing differential equation of a cantilever bar subjected to uniformly distributed load. So we got the governing differential equation. Now we have to solve the governing differential equation. In order to solve the governing differential equation, we have to define the boundary conditions. So let me define the boundary conditions. At the left extreme end, what is the value of displacement at the left extreme end here? 0. So displacement at the left extreme end is 0. What is the value of strain at the right extreme end? Strain is du by dx at x is equal to L at the right extreme end. That is also 0. Why it is 0? It is for exactly the same reason that the foot of the last person here is, he is going to experience 0 strain on his foot, 0 stress on his foot. And it is exactly for that reason the strain is going to be 0. So these two are the boundary conditions. U of 0 is equal to 0 and du by dx at x is equal to L is equal to 0. Now let us see how we can solve the governing differential equation, but before that you may fancy the idea of a short break. Thank you.